Hello, hello, everyone. Happy Tuesday, wherever you are joining from in the world. So happy to have you here with us today. My name is Heather Grant. I am one of the community admins at the Maintenance Community by Upkeep. Thank you for making the time to join us for today's webinar. If you are not already a member of the Maintenance Community on Slack, we would love to have you join us there. I will add a link in the chat to sign up in just a moment. Today, we have Jesus Cifante joining us for a presentation on using Weibull analysis for fine-tuning RCM decisions. Technical topic, but it should be really, really informative. I'm excited and looking forward to it. I'll let Jesus introduce himself, tell us a little bit more about him and his experience in just a moment. But again, I'm really looking forward to our conversation today. The recording from our session will be available in the maintenance community on Slack, as well as at this link right after we end. So please feel free to share either the recording of this webinar or the invitation to Slack directly with anyone you know who would benefit from hearing some of Jesus' expertise. Last piece of housekeeping, then we'll go ahead and get started. You'll notice that your cameras and microphones are not turned on today. So if you have any questions for Jesus as we go throughout the presentation, please feel free to drop them in either the chat box or the questions tab over on the right-hand side of your screen. We'll do our best to get through as many questions as we can, but anything we don't get to, we'll be sure to answer offline in the community as well. That is all from me. Thank you again, everyone, for being here. Thank you, Jesus, for taking the time to join us, and I will turn it over to you to get started.
Thank you very much, Heather, for having me again here. It's a real pleasure to be here, and I see that we have people from that I've seen before. I know that we have people from other parts of the world, and I'm very excited about that, Heather. So I would like to have our attendees sharing with us where they are getting connected from. So that motivates us to continue spreading the message and speaking about good practices, knowing that we are getting very far away with our messages. So I'll speak today about using Weibull analysis for fine-tuning RCM decisions. So first I will introduce myself. My name is Jesus Cifante. I'm working with the Conscious Reliability here in Toronto, Canada, and I am also the president of PDM Tech with operations in Puerto Rico and here in Canada. So we'll be speaking about RCM and also about Weibull analysis concepts, and we'll see how the two of them can work very well together in a model called RCMR, and we of course will see some examples that I have to share with you so you can see how the two of them work very well together. So I won't be, it is not fair if I don't mention a couple of publications here that have helped me to master or to understand these topics. First, machine condition monitoring by Ray Beebe from Australia. He was one of my professors in the master degree of maintenance and reliability engineering with Monash University. So I'll be using some info from that book. Also, Weibull Analysis Handbook from Dr. Abernethy, which is the real master in Weibull analysis in this part of the world. And of course, my publication and James Regis Picknell publication on RCMR, which is a model using RCM together with other quantitative techniques. So let's go ahead and start speaking about RCM. So what it is, and I would like to see how many of you have experience with RCM. Tell me something. I would like to have some words from you in the chat. If you are familiar with RCM and you are also familiar with Weibull analysis, let us know in which role you have been participating. So I have people here from California and from Los Angeles, etc., and from other parts of the world. That's fantastic. So let us know what has been your experience with RCM. And Martin's from Nigeria and other guys that I've seen very often in our community. Welcome. So what is RCM? Well, RCM is a systematic process to determine what we have to do in order for asset to continue doing what their owner need them to do in the current operational context. So we're speaking of a methodology that is very high end, that is intended for critical assets, and it will help us develop, among other things, maintenance plans. So we will develop tasks that are prioritized according to their consequences, meaning that we have to do a risk analysis when we apply RCM. And each of the tasks has to target specific causes, implying that we need to do also a kind of root cause analysis while doing the RCM. So we also do other decisions. We make other decisions like redesign type of decisions. We may need to design some procedures, processes, practices that we see that are not proper, that are hindering us from gaining the best results from our maintenance program. We may also need to do design changes, and sometimes we may decide that some particular failures had to happen, and we will deal with the aftermath. So this is what we get from an RCM analysis. And remember that I told you that RCM is intended for high criticality assets, implying that before applying it as a strategy, we need to do a couple of things before that. So one of them is an asset criticality assessment to make sure that we apply RCM to the right equipment, to the right assets. So when can RCM be applied? I get that question very often. And for that question, I will tell you that do it as soon as possible, provided that you select the right equipment and the right methodology to do it. So let's just present briefly. This is a very brief summary of the RCM process uh, diagram. This is a very simple diagram. See the starting point here. So if the first thing that we do when we apply RCM to an asset is establishing functions or listing the asset functions according to the standard, then we determine the fail states, excuse me, then we list all the possible failure modes. We evaluate the failure effects. We classify those effects into consequences. Then we determine proactive tasks, and we may recommend some default actions if we are not able to find a proactive tasks that are feasible. And this is then when we implement, we go into a continuous improvement process. So basically here from the starting point up to 1, 2, 3, 4, 5, 6, 7 to here, we have already answered the 7 basic questions of RCM. So if you are familiar with the process, you will see that you will be producing a kind of work like this. This is a worksheet from an RCM analysis. This is not an Excel worksheet. This is actually a software that help us implementing all the analysis or doing all the analysis. So here you see that you have your functions. Your asset has primary, secondary, and hidden functions. You just mentioned all of them with your multidisciplinary team, and then you have your fail states for that functions. For those functions, you may have total and partial failures. You mentioned them all. Then you have your failure modes, and in the RCM model, we even break down break them up into failure root causes. So then when you mention your failure modes, you do the failure effects analysis, which is a statement explaining how the failure occurred, and then you do, if you want to do a quantitative analysis, you apply a risk matrix in order to get the criticality of each of these failure causes. From here to this column in colors, we have answered questions 1 to 4 of the RCM process. And here in the task column, we have answered questions 5, 6, and 7, which is the consequence, the type of task, which is the failure consequence management policy. We know that the RCM process helps us decide on these failure consequence management policies that we find in the far right end here, but we need to develop tasks from these consequence management policies, and then we develop specific tasks with the corresponding frequencies of application, and we also recommend uh, people to do the task. So this is basically the RCM, how an RCM analysis worksheet looks like. So there are many benefits stemming from a well done and properly done RCM analysis. There are economical type of benefits. You will save a lot of money in unnecessary PM time. You will reduce a lot the safety and environmental and costly breakdown failures, and you will get motivation, more motivation from your people participating in those analyses, and of course, all the KPIs, maintenance KPIs, will look better for a company. There are many benefits that you get for a very well done RCM analysis. So what about Weibull? So I just presented briefly what RCM entails. Remember that it is a process to determine what to do for assets to continue doing what their owner need them to do. So that is basically RCM. You have to answer 7 questions as established by the standard SIG 8 and 11. And it is the endeavor of a teamwork, of a multidisciplinary team for determining those tasks. What about Weibull analysis? Weibull analysis is completely a quantitative type of analysis, meaning that we need to have numerical data. We need to have field data in order to apply the analysis. Dr. Abernethy, in his magnificent RCM book, says that these are presents these type of applications that I have here, I listed here as the general applications of Weibull analysis. You can use Weibull for predicting failures, for evaluating corrective action plans, and so forth. You can forecast spare parts. You can apply to calibration of complex systems, and you can do a lot of things with Weibull analysis. And why is that? Why is Weibull analysis so important? Many people ask me, Jesus, why do you stress so much attention to Weibull analysis? And my answer is because it is simple to use and very effective. And you don't need a lot of data to create a very effective model to predict failures and to enhance your maintenance program, to be able to select the right type of task based on how things are happening on the floor. So that's basically how it plays. So it was developed in 1937, and Mr. Weibull, Walody Weibull, which was an engineer, a statistician, and from Sweden, so boasted that his model was capable of providing very effective forecasting capabilities with just a very small population of events, and that's music to our ears in maintenance. We don't want to we don't want to have many failures in order to create a model. Just a couple, 2 or 3 events, we are able to put together a model that makes a lot of sense to us for improving our approach, maintenance approach. Remember the following, bearing in mind the following. Weibull analysis applies to simple failure modes. It doesn't apply to the whole machinery. You have to go to failure modes, the listed failure modes, and then find data that is relevant, that is related to those particular failure modes. In other words, if you want to apply a Weibull analysis to an electrical motor, you will have to break down the motor into components. Say I will do an analysis to the bearings separately from the coupling, from the oil seal, from the whatever wiring, etc. So we first need to break down our components of our machine into components, and if we use the RCM sheet, so we will just go and apply to the particular failure modes. It is a plot of age here. In the you have age in the x, uh, and in the y coordinate you have probability of failure. So in the abscissa you have time, and you have then probability of failure in the y in the y axis. So by age, we mean you can use hours, operating time, but also you can use other units, other measures of usage like kilometers or mileage, for example, cycles, processed, lots, etc. Any parameter that implies age, you can use here in the x axis. And in the y-axis, you will use the probability of failure. If you don't comply with points 1 and 2, the plot itself will tell you, because the points in the plot won't be able to be crossed with the straight line. They won't fit into a straight line, and it means that we get curvy type of Weibull plot. That means that there's something we're not doing well. So we can create probability plots. We can determine the reliability and probability of failure levels at any operational time. We can determine predominant pattern of component failure, and we can confirm the proper selection of task. That's what I will explain to you during my webinar. And if there is interest in the future, we can even explain to you how to calculate frequencies based on Weibull analysis. So these are the main functions of Weibull. There are other two that I won't be covering today because of time, but the first one is the reliability function equals e to the power of time over eta. Eta is the scale parameter, and I will tell you briefly. Yeah, I will tell you in a minute what it is. Then we have beta elevated to the power of beta, which is the shape parameters. These are the two main parameters, or the two parameters of the Weibull function. Then we have the probability of failure, which is 1 minus the reliability function. 1.10, 11.10 and 11.11 means that you will find this information in our book, RCMR, in chapter 11. So these are the corresponding graphs for the reliability and probability of failure functions. See that reliability vanishes with time. It goes away with time. So when you speak about the reliability of a component, you necessarily have to mention at which time, right? So reliability at 500 times is less than the reliability of the same component at 100 times at 100 hours time. So you have to, it is related to time. So it vanishes with time, the reliability and the unreliability or probability of failure will continue to increase with time. So these models you create with the Weibull analysis, these are the models you create. But you will be using a different type of plot. So instead, our graph won't be curvy like this one's. When we do Weibull analysis, we are going to use a special paper to do the plotting, which is logarithmic with both scales, x and y axis scales logarithmic, and the the course and the resulting model will be a straight line which we analyze. So we have here the shape parameter beta, which correspond to the slope of this line, which is the resulting line from the analysis, and I will explain to you how to we plot that line briefly. And we have the scale parameter eta, which is the characteristic life or the typical life of that component. And I will tell you briefly in a while how do we find that into the graph. So these are, when we do a Weibull analysis, we are mainly looking for beta and eta. That's what we are looking for. And then we do an interpretation of those results. And if beta, for example, is less than 1, means that you are having premature failures. That's how we interpret the plot. If beta equals 1, we are having random failures, and if we have beta greater than 1, we are having wear out type of failures. That's the way of interpreting the plot. And look that we have here an actual plot, Weibull plot. This is for some bearing data. And see that somebody plot points here. Is that person draw a straight line here, and this line correspond to the Weibull plot. Now, after plotting the line, it's time to interpret it so we can understand what the model is telling us. So look at the data here. So we have 10 failing times here. So it means that it could be applied to 10 similar bearings with the same application, or the same bearing that has failed 10 times. As long as the bearing type and is the same with the same operating context, we can include the data together in the same analysis. So look that we have the age at failure. It has been ordered by age from 300 hours to 1200 hours of operation. Then we calculated the median ranks, which is the probability of failure. How do we do that? There is a little formula here called the Bernard equation that we use. The median ranks equals I, and I is the event order. So we have from 1 to 10 here. Ranging from 1 to 10 is the order. For event 1, we will use the number 1 here, and then becomes 1 minus 0.3 divided by n, which is the total number of events, in this case 10, plus 0.4. When we do this operation, we obtain 0.068, which we multiply by 100 to convert it to percentage, and we get the median rank or the probability of failure for that particular age. We do that for all the points, and what we then do is that we plot them one by one. See here? So now I'm doing it for the first point. See the X here? You do it for the second point. So you have the coordinates here for each of the points. 300 is plotted against 6.8. Then the following 410 is plotted against 16.2, and so forth until you plot all the points. Then you cross the points with a straight line, as I just did here. And now you analyze the characteristic of that line. So the first thing that you look for is the slope. So what is the slope of the line? The slope of the line is exactly beta. Beta is the slope of the line. That inclination tells you if your failures are happening randomly or prematurely or in a wear out fashion. So in this case, we have a slope here, beta value of 2.5, meaning that we have wear out type of failures because beta is greater than 1. The second thing that you look at when you do the Weibull analysis is the intercept here of your model line with the dot line crossing the paper horizontally here at the 63.2% probability of failure. So here you look at this intercept, you drop a line up to the X axis, and you will find that your characteristic life is exactly 825 hours. So these you have already calculated, determined your Weibull parameters. I say calculated, but you haven't done any calculation. Everything is done graphically. So you see that just by inspecting the graph, you do the analysis and you determine the parameters. So if you wanted to know the probability of failure at any age, you can just do it you can do so by inspection. Let's say that Mr. Lucas Marino, which is in the audience, my dear friend Lucas Marino, tells me, Jesus, how much is the probability of failure? What's the value for the probability of failure at 400 hours of operation? What I'll do is I will just stop here by the 400 hours, and then we'll go up here, up until I just touch the model line, and we'll then throw a straight line here to the left, and I see that it is about 15%. So you will, with the Weibull analysis, you have an idea of the probability of failure at any age of the asset, of the component in particular. If you know that 15% is the probability of failure, indirectly, you know the reliability level, which is the complement, right? It is going to be 1 less 15%. So at this point, you have an 85% probability of failure. So that's how you deal with the Weibull plot. So in our advanced RCM classes, we do all these plots by hand. So people use the Weibull probability plots, and they do their analysis, and they apply it to particular failure modes stemming from the RCM analysis. How do we integrate the two things together? So we do that in our RCMR model, and I will explain to you quickly how we do so. So in our model, we have RCM embedded into the asset management concept, meaning that there are things that we have to do before we apply RCM if we want to apply it in a strategic way. So we first do some data integrity analysis to make sure that the data that we are going to use is meaningful and is good data. We also do an asset criticality analysis just before doing the RCM analysis, so that to make sure that we apply it to the right assets, and we have good data to make the analysis later on. When we start doing the RCM analysis to a particular asset, we go then to the second sub-process, which is the RCM process analysis by the standard. And while doing so, and we are going to do the decision analysis, we then ask ourselves, do we have data? Do we have data backing up our opinions here? Then the planner tells us, yes, I have some logbooks, and I have here some very good information for you, and you have failing data for this and that component. And that is at that point we apply the fine tuning, and we correlate failure modes with their corresponding data from the field, and we can fine tune the decisions. Because one of the very common pitfalls when doing RCM is assuming that all failures happen by age, that all components enjoy having a useful life, and that always will happen. So that they have a long period of operations, and will break by normal degradation. And the RCM standard, SIJ 1011, encourages us to analyze three types of failure modes. First one is, of course, natural degradation. The second one is design flaws. And the third one is errors or mistakes by operators and by maintenance itself. So we need to investigate what the data is telling us. So when we go to this stage of the analysis, we have a couple of different analyses. We have some KPIs stemming from the same data. So we have a good understanding of the availability level of our asset as a unit to see if it is in compliance with what the owner expects from it. We have some reliability analysis at a glance with MTBF and maintainability indicator as well. But we can do the Weibull analysis to the failure mode level. Look that the first analysis here is done at the asset level, at the system level, but this 8.2 analysis is the Weibull. It is done at the failure mode level and will influence the outcomes from our analysis. So you may, if you were to suppose that everything fails by a natural degradation, then you will never recommend any redesign because everything degrades by time. So I will apply condition monitoring or time-based maintenance to everything, and I forget about the mistakes, I forget about the errors that people make, and about the design flaws. So then we will decide the right strategy. When doing the Weibull analysis, we can fine-tune even the strategy. These here are different strategies. F means run to failure, R means redesign, D means detection or failure finding, 2 is a combination of tasks, T is time-based, C is condition monitoring, and O means tasks assigned to the operator. So we have to look at the data to finally decide which is the best approach from the maintenance perspective. And if we have good data, we can even do a good task selection, and we can calculate the frequencies for those tasks very, very accurately. So let's take a look at some of how Weibull analysis work can be applied to an RCM analysis. So remember that when you apply RCM, the first thing you should do is sorting the data, the failure data, by age. Thing is that if you look at your CMMS, you will find data is being input chronologically. So you will have the most recent data is the data that you have from last week, but that is not necessarily the more, let's say, aged data. You may have a failure from last week that occur at a very short period of time, and the things that you need to go ahead and order that data by age. Weibull doesn't work with Chronos. It doesn't work with your calendar. You have to translate all the failures into aging into age. You have to order by age. So that's the first thing that we do. Then we determine the probability of failure or the median rank for each of the failing times, and then we do the graph the plot as I explained. So let's take a look at a couple of examples. But before that, let me just review with you how to assign the proper maintenance strategy according to the Weibull analysis. Let's say that we do a Weibull analysis and we end up having a beta value less than 1. That means that we are having premature failures, and we cannot recommend any maintenance task, like any proactive. We cannot recommend condition monitoring, or we cannot recommend PM time-based tasks for tackling a premature failure. If we had, for instance, random failures, we are not, let's say, the good practices do not allow us to recommend PM, for example, time-based, because random means that it is not dependent on time. It can happen at any time. So PM is not good for random failures. If we had, for instance, a beta value between 1 and 3, it means that we have a combination of random and wear-out failures altogether. And that's the perfect scenario for condition monitoring. If you had a strong wear out, meaning that beta is much greater than 3, that's the perfect scenario for a time-based restoration or an overhaul, because failures tend to occur more or less at the same time, and you have a very steep slope in your Weibull analysis. So this is pretty much the interpretation of the Weibull parameter beta, which is the most important, and how to correlate maintenance strategies according to it. So let's take a look at an example here. So I brought 3 examples, different types of. The first one is a clog strainer. So this company has some records of failures for a strainer of this little pump here. So the first failure occurred at 401 operating hours. Chronologically, this was the first failure. It was changed or cleaned, and then it was put in place again and failed almost 300 hours later. And the third failure occurred 505 hours afterwards. So we have 3 failures here. They are presented here chronologically, so we have to rearrange them into in order of age. So we are to determine beta, eta, the predominant failure pattern, and also determine the adequate task type for tackling this failure. So the first thing we do is we have to reorder the events per age. So the second event here, which was 298 hours, now it is ranked here first. So this is the ranking order. So the second one will be 401, the third one will be 505. We calculate the median ranks with the Bernard equation, and we already have the coordinates for each of the 3 points that we need to plot. I am using the Dora RCMR software here to plot these 3 points and see that we have them plotted here. This is 300, 295 and 98 against 21.2 and so forth. Once we have the 3 points, a straight line is drawn, and now we just look at the slope of the line, telling us the beta value. See that we have a very steep value of beta here, and the eta value will correspond to the intercept of this line here, 63.2% of failure with the line of the model. So because all of the results are here very small letters, I just enhance them for you to see it. Beta equals 3.6 and eta equals 445. That means that we have a very steep beta greater than 3, and now since we have a strong out, very strong wear out pattern here, we can use time-based maintenance. And we are certain the data is telling us that this type of strategy is going to work for us. We have an eta equals to 445, so we will use that number in order to calculate the frequency of that change together with some economical data, and we blend it together in an equation that I will be very glad to explain to you in another session, how to calculate the frequency, the optimal frequency for that replacement. So here we have beta 3.65, eta 445, a very strong wear out pattern, and we selected a task type T because we are certain that failures are happening in a very small range of time. Let's take a look at another situation here. This chemical plant wants their PM for the centrifuge being revised, especially the filter change for the unit. They have experience for failures, and these are the corresponding failing times: 169 hours, 20 hours, 74, and 350 hours. Let's do the Weibull analysis to see if we can recommend a replacement by time or a cleaning by time, or what do we have to recommend here. So we do the analysis, we order the events, right? We determine the median ranks. Now we have the coordinates for the 4 points to be plotted, and see that now we don't have such a steep line now. It is kind of flatter. So we suspect that we don't have a strong wear out here. You see the range of time between the first and the fourth failure is very wide one. So let's see how the analysis plays. It says that we have beta equal 0.8. That is less than 1, so we are having a premature failure. There is something wrong here. Either the cloth is not the adequate, or the process of installing it is not the adequate. We may have some machine design problem, or we are not using the proper tools, or our mechanics are not trained, but something is going wrong with this, and there is no maintenance task that will resolve that until we do some redesign analysis. So here is where I would like my friend Lucas Marino doing the maintenance task analysis to see what kind of tools we need, what kind of procedures we need, because there is something wrong with this machine, and maintenance cannot solve that. So on the fly, I will answer a question: what is MR? How to calculate MR? Let me go back and present it quickly. MR is calculated like this. So Mr. Felix, so MR is calculated like this, equals the median rank equals this is I less 0.3. I is the order of the event. Once you reorder the events, this is the last order. When you reorder the event, for the first event it's going to be 1, and for the last event, in this case, since we have 10 events, it's going to be 10. And n, it is going to be a constant, which is the total number of the events. So for all of the calculations, you will use 10 in the denominator, and when you substitute the numbers here, the only thing you will be substituting here is I, which is from 1 to 10. So, and you will do the calculation and we'll get the median rank. So I saw that question in the chat and I just wanted to, on the fly, answer it. So let's go to the third example. We have here a motor bedding wear. We have the tendency, we are very tempted to assume that all bearings fail naturally by age, and the right thing is that the real thing is that bearings, most bearing, maybe 80% of bearings fail before the design intended design time of life. And why is that? Wrong practices, wrong selection of the bearing, wrong lubrication, misalignment, many things affect bearings life. So we want to make sure that we don't have premature failures and that we don't have random failures with regards to bearings. If we are certain that we don't have these two types of patterns, then we are certain that condition monitoring or maybe other type of maintenance strategy will do the job. Let's see how it plays. So we have here the model for these 4 points. So see that we don't have such a very steep line. So the slope is not like 3 or 4, but it is not less than 1 either. So we are in the vicinity here of 1, between 1 and 3. So here we are having a 1.96 value of beta, and eta is almost 3,400, 34,000 hours of operation. So beta being let's say 2, and eta being 34,000. So the beta value tells us that we are having a random and wear out type of failure, which is very typical of bearings. So we will, the task type will use, if it's not right, we have to use here condition monitoring for tasks. So I will live here, correct it, and we'll go back and present it again. Okay, so I will just project it with the right result. I will share it with you right away. Ta-da! We have it correct now. So since our beta value ranges from between 1 and 3, it is in the range of 1 and 3, is exactly 2. So this is the perfect scenario for condition monitoring. So we are certain that our bearings will respond very well to the way we operate it to a condition monitoring task. If, for instance, we were getting data less than 1, it means that we are facing premature failures, and we will need to change our practices, study our practices. So let's summarize. We have spoken about RCM and the standard SCI JEA 1011 very briefly because we have a 3 days class for that, and we just explain it in a couple of minutes, but we try to do our best. We also spoke about the enhanced RCM process, RCMR, entailing 4 subprocesses, including fine-tuning of the data as one of them, the fine-tuning of the RCM decisions with Weibull analysis as one of them. We explained very briefly how to do an RCM and a Weibull plot and how to interpret it, and we presented 4 examples. So I would like to thank you for attending the webinar, and I will turn my attention now to the chat and see if I can answer a couple of questions there. And I really appreciate you attending here and your comments and your greetings, and that is very satisfying for a speaker. So I'm taking a look, Heather, to the questions here.
Yes.
And to see how, in my best knowledge, I can answer them.
Yeah.
If I can't answer them, I will shoot them to Lucas Marino, which is in among the audience, for he to answer them. So I have comments here. I have a big fan from Virginia here. Let me see, from Portugal. From Portugal, obrigado. From Mexico, Hector. Hola, Hector. Gracias por venir. So, how much is the probability of failure? Okay, I have a question from Mr. Marino. If we want to determine the probability of failure by using the model, I will show you right away. So the only thing you have to do is look at the straight line here, and you determine at which point in life you want to know that probability of failure. Let's say that you wanted to know it exactly at 50,000 hours. So you will just start here at the 50,000 hours line. We'll go up here. You will touch the model line, and now you throw a line to the y-axis and see that your probability of failure is almost 90%. So you are 85, 88. You have a probability of failure of 85 to 88, just by inspection. That's the level of probability of failure that you're having. If you wanted to know the reliability, it will be the complement. It will be 100 less 85%. So you have about 15% of reliability at that age. On the other hand, if you wanted to see that, if you go down to a less time, so let's say that you wanted to know the level of probability of failure at 40, 30, 20,000 hours of operations, then you have about 30% probability of failure, which is 70% reliability. So just by inspection, so it is very easy to do. So it is more difficult to find good data to do the Weibull analysis than doing the analysis itself. So there is a very strong relationship between the work order documentation. When our technicians do their corrective work in the field, we need to have good data from them. So the type of failure they found, that's a failure mode, the age of the component that's failing, all that information is like the material, that the raw material that we need to do a Weibull analysis. So it comes from, the floor, from the data that we receive from our guys in the field that would enable us doing analysis for improving reliability. So I have a comment here from Francisco Saldivia. I happen to know some of these guys writing here, like Mr. Lucas Marino, like Mr. Saldivia. Thank you very much for attending. He's making a comment here. When you apply Weibull analysis, when it is applied to a complex equipment, you will have always beta equals 1. That's right. So that's why it is better if you apply it to simple components. Because when you apply it to a very big system, everything happens randomly because you're having electrical, electronics, mechanics, hydraulic systems all together being analyzed, and it always will tend to be 1, the beta. So you should break down into more failure modes. Can anyone carry out Weibull analysis, or only the reliability engineer who is responsible for this? Okay, who is able to do Weibull analysis? Whoever has the data. So if you have the data, it could be done by a supervisor, it could be done by the reliability engineer, it could be done by the maintenance engineer. The important thing is to have data, but it is the endeavor of a reliability engineer to just study failure data for continuing improving reliability. So Andre has a comment: is the primary purpose of Weibull analysis like a categorization of maintenance type? It is just one of the applications. Weibull has a lot of applications, even out of maintenance. So we take advantage of its capabilities to give us good results with just little data. So Francisco, you're very welcome. Saludos. So Mr. Lucas Marino, thank you very much. Thank you, Solomon, for your comments, and everybody for attending, for being so kind with me, with your comments. Okay, what's the most common application of Weibull for maintenance? So I love that question because we do a class which is reliability engineering applied to maintenance, which is the many ways in which Weibull and other analysis can be helpful in maintenance. So there are a couple of ways. So the first thing is that Weibull analysis lets us understand the prevailing pattern of failures of our components. So that way, if we understand the physics of the failure, we can choose better tasks, the appropriate tasks to tackle them. You can even stop doing maintenance until we understand very well why failures are occurring, and then when we make the proper correction, then apply the corresponding or the right maintenance to do so. Secondly, we will choose the right maintenance task, and it enables us to calculate the frequency of those tasks properly, but we need more information to do that. We may need some cost information, we may need some risk information, and that is part of the Weibull, of the benefits of doing Weibull. The Weibull analysis will also enable us to understand when to do redesign to the machine, when to revise our procedures because they are not effective, and we are getting like premature failures or random failures when they are not wanted. Yes, Mr. David, Trones is telling something that is very truth. So we need to have good data. We need to have good confidence bands. The better the data, the better the confidence bands that we have when analyzing statistically the data, the best we can do analysis, the best we can do decisions with them. So
Awesome. Cool. Well, that is perfect timing. If there's, when is the next webinar for Weibull going to be?
so thank you very much, and I will just
We'll
have
get
a
to planning.
yeah whenever Heather invites me again.
Yeah.
So I'll be willing to do that, and just you can contact us here at this. You have my email here, and you can contact also Heather, and we will be very happy to come back with you guys. You are lovely. Thank you very much for all the comments and for attending from many parts of the world.
Yeah, I had a great time. Thank you, everyone, for joining us today. Thank you once again, Jesus, for taking the time, sharing your knowledge, and going through that Q&A. I know that's always a helpful piece for our live attendees. So thank you, everyone, and we'll see you all next time. Bye-bye.